Welcome to lecture number 5 for ECE 111, Introduction to ECE. In this lecture, we look at using MATLAB to analyze renewable energy, specifically wind energy and solar energy. So, kind of as a recap, back in lecture 4, we were looking at curve fitting, and we could curve fit global CO2 levels, global temperatures, the Arctic sea ice, and what we saw is that the CO2 levels are going up, the temperatures are going up, the Arctic is melting, and this has happened before, and the results were not very good. That's sort of what triggered the Permian extinction. With the Permian extinction, CO2 levels reached 2,000 parts per million, global temperatures increased by 10, then 20 degrees Celsius, and the ice caps all melted. The result was that pretty much everything bigger than a mouse became extinct, and it took 10 million years for the Earth to recover. On the planet Venus, currently it's hypothesized that Venus was very much like the Earth at one time. However, it had a similar experience as the Earth with the Permian extinction, except that it didn't recover. It had runaway global warming, which results in a dead planet. So that's kind of depressing, but there is good news. There are ways around it. So one question is the global warming man-made or not? Well, if it's not man-made, we're basically hosed. If it is man-made, then we can do something about it. And one of the ways that we're causing global warming is our CO2 emissions. This is a graph of the CO2 emissions per year in gigatons per year. And as you can see, the CO2 emissions are just skyrocketing. CO2 is a greenhouse gas, warms the planet. If we want to avoid the Permian extinction-like events, we need to cut back on our CO2 emissions. There are ways to do that. The main source of CO2 emissions are coal, oil, and gas. If we quit using coal, oil, and gas, that'll go a long way towards reducing our CO2 emissions. And in terms of use, for the U.S., the main cause of CO2 emissions by use is 25% is from generating electricity, 23% from industrial use, 20% by transportation. Well, these are all things we can do something about. If you switch to electric cars, we can get rid of the transportation emissions. If we switch to wind, solar, and nuclear energy, we can get rid of the electricity. And you can do a large part of getting rid of the industrial emissions as well if we have cheap, clean electricity. So there is something we can do about it. In order to move away from fossil fuels, we've got to start embracing solar energy, produced energy using photovoltaic panels. And the nice thing about that is that provides jobs for ECE majors and kind of saves the planet. But really, we get jobs. There's wind energy. Wind energy produces electricity using the wind and also provides jobs for ECE majors. There's electric vehicles. You can have transportation without CO2 emissions, and that provides jobs for ECE majors. And you can switch from incandescent light bulbs to LED light bulbs. That reduces the country's energy demands by about 40% and provides jobs for ECE majors. So there is a kind of a silver lining to all this. If you care about the environment, care about the planet, want your kids, grandkids to have a habitable planet, electrical and computer engineering is a really good major to choose. You also make money. In engineering, you almost have a guaranteed entry into the middle class. You have a lot of fun building toys that makes people's lives better and actually may save the planet. So if you care about the planet, care about your kids, care about your grandkids, if you care about the future, you picked a really good major. ECE is a great major for that. On the other hand, if you don't care about the planet, your kids, your grandkids, or the future, ECE is still a pretty good major. So you picked a good one. In this lecture, we're going to cover renewable energy. Basically, on lecture 4 was kind of depressing. We can't leave it at that. We're going to look at some ways you can actually try to get away from greenhouse gases, get away from fossil fuels. We're going to look at solar energy and wind energy. Using MATLAB, we'll determine the energy produced out of a set of solar panels. Using MATLAB, we'll determine the energy production from a wind turbine. And then we'll start asking questions, such as, is solar energy a good investment in Fargo from a purely financial standpoint? And what that means is a common rule in business is if you make an investment and it pays for itself in 7 years or less, then it's a good business decision. We'll look at, is wind energy a good investment in Fargo from a purely financial standpoint? Meaning, does a wind turbine pay for itself in 7 years or less? If you take into account that you might save the planet as well, it has other reasons to do it, but we're just going to look at a pure financial aspect of it. So let's start out. Let's look at solar energy. Suppose I want to put solar energy on my house. Well, if you go on eBay, you can buy solar panel kits ready to go. For example, this is one that I found in 2023 summer. It's $19,000 to produce 16 kilowatts of solar energy. Is that a good buy? Meaning, if I put that on my house, how much energy would I produce on a yearly basis? How much money would I save on a yearly basis? And would solar panels pay for themselves in 7 years or less? So these are the questions I want to answer. How much energy am I going to produce? What's the total energy that will produce in kilowatt hours? How many pounds of coal that offsets? And how long I have to wait for the panels to pay for themselves? And we'll look at two different cases. One, you live across the river in Moorhead, Minnesota. Minnesota has different laws than North Dakota. Minnesota has net metering. And what that means is that if I produce 1 kilowatt hour at noon and then use 1 kilowatt hour at midnight, I owe nothing. Or if you live in Fargo, North Dakota, which does not have net metering, so if I produce 1 kilowatt hour at noon, I get 2.8 cents. If I use 1 kilowatt hour at midnight, I pay 11 cents. How does it work out in Fargo? So the first thing you need to do is we need to get data. So if you go to ndsu.endon.edu, this is what the Endon website looks like. This is actually a website from the North Dakota State University Department of Agriculture. And what they're doing is they're monitoring the weather at different spots across the state and in Minnesota. They're looking for conditions for fungus growth. So if I pick one of these, like Sawyer, North Dakota, let's see. Better yet, let's pick Rugby, North Dakota. This is what the weather station looks like. So it's got a solar meter to measure the light intensity, measures ground temperature, ground moisture, wind speed, wind direction, rainfall, all sorts of things. So if you see these around the state, that's part of Endon. Leave them alone. This is actually a really nice website. If I want to collect data, I can go collect on weather data. And we're going to take the monthly, actually hourly data. So I want to get hourly data. Pick your favorite station. So I could do Fargo or Rugby. Pick anywhere you like. Let's just say Rugby. Rolla Rugby. There we are. Rugby, North Dakota. And you can collect any of these data sets. Right now we want to look at solar energy. So let's look at solar radiation and pick your time frame. Let's say for the last 4 weeks. I can now switch to metric. You make sure you're in metric because English units are just a pain to work with. Here's the date, the hour, and the solar intensity in megajoules per square meter. Click on Export CVS file. Time passes. And then open it. Okay, so eventually it opens up. What I want to do is grab this last column. So this is the location, the latitude, longitude, elevation, date, hour. here's what I want. So let's do a copy. I'm going to select all the data. This is a great thing about the internet. You don't have to sit there and type in all this data, which would just be a pain in the tush. Select all the data. Good enough. Copy. Go into MATLAB. Say data equals start of matrix, paste. And that was Control V to paste. The old WordStar commands, Control C is copy, Control V paste, square bracket to end the matrix. Then I can plot it to make sure I got the data in. And that's what it looks like. This is the solar intensity in Rugby, North Dakota for the last couple days. So here you can see it's nighttime, daytime, nighttime, daytime, nighttime. You can see the days and nights go by. And it looks like a couple clouds came by over here. So that's where you pull in the data. So that's kind of the procedure. Go to End On, select your favorite city, select what you want solar radiation total, and go over time frame. In MATLAB, I can then copy and paste. In this case, I'm going to say megajoules per square meter is start of matrix, paste, end of matrix, and plot it. I always like plotting it to make sure I got the data. The data is correct. All right. So let's look at these solar panels. The energy or the units are megajoules per square meter. I want to convert that to kilowatt hours. Well, if I assume 80 200-watt eco-worthy solar panels to produce 16 kilowatts, the area of the panels, going to go to eBay, look up eco-worthy solar panels. The area is 1.48 meters by 0.67 meters each times 80. I've got 79.328 square meters. That'll tell me the total megajoules coming in on these solar panels. Now, solar panels aren't 100% efficient. They only convert 21% of the energy into electricity. And the reason for that is if you look at the energy of sunlight, the energy does something kind of like this. With the solar panels that are made out of silicon, I take the electron gap voltage, something like this. Any energy less than this is lost. Any energy more than that is enough energy to kick the electrons out of their covalent bonds and produce current flow. But all the energy beyond that threshold is lost. I only get this much energy out. So you're never going to get 100% efficiency. Turns out these solar panels are about 21% efficient. That's actually not too bad. If you look at nature, nature also has solar panels in leaves and chlorophyll. Chlorophyll is right around 0.1, 0.2% efficient. The world champion for plants in terms of efficiency is sugarcane. Sugarcane is 8% efficient at converting sunlight into sugars. Solar panels are 21% efficient, so we're actually better than nature. But then we have a slight advantage. We don't have to worry about metabolism. So anyway, solar panels are 21.5% efficient. And converting megajoules per square meter into kilowatt hours, I can do this equation. 1 megajoule per square meter, get the meters to cancel. I've got 79 square meters, so these cancel. 1 kilowatt hour is 3.6 megajoules, so these cancel. And I'm at 21% efficient. So 1 megajoule per square meter of sunlight is going to produce 4.73 kilowatt hours every hour. So there's my conversion. To convert from megajoules to kilowatt hours, I multiply by 4.7376. Then if I plot it, let's plot kilowatt hours versus hour. I've got 720 data points in my array. Size is a MATLAB command that tells you how large your matrix is. So hours are going to go from 1 to 720. If I plot hours divided by 24, that gives you days versus kilowatts. That's what I get, the blue lines. So this is how many kilowatts I'm producing on an hour-by-hour basis over the month of April 2023. To find out the total amount of energy that I produce, add it all up. That's integration. The neat thing is this is sampled every hour. So take the kilowatts times 1, I get kilowatt hours. Add them all up, the total kilowatt hours is 2428.1. That's how much energy I would produce during the month of April 2023 using these solar panels. So here's some questions. What is the hourly energy production for these panels? Well, that's the blue curve on the last page. What's the total energy produced over the month of April 2023? That's just add them all up. That's the MATLAB command sum. It's actually sum times 1 because it's sampled every 1 hour, but also just sum. So I produced 2428 kilowatt hours over that month. How many pounds of coal does that offset? Well, if you go to the Minn Kota 2019 annual report for Milton Young Power Plant, it tells you how many pounds of coal it used that year, how many kilowatt hours it produced. Take the ratio, you get kilowatt hours per pound. So Milton Young Power Plant uses 1.78 pounds of coal to produce 1 kilowatt hour. So take the kilowatt hours times 1.78, that's how many pounds of coal you offset. The solar panels on my house would offset 4,322 pounds of coal every month, at least in the month of April. How long does it take the panels to pay for themselves? Now that's the economic question. That's the real bread and butter we're looking at. Well, that kind of depends. Where you live, who your utility provider is, what plan you're on. Let's start out, let's assume I live across the river in Moorhead, Minnesota, and I get my energy from Xcel Energy. Now in Minnesota, they have net metering, and what that means is that if I produce 1 kilowatt hour at noon, put it on the grid, then I use 1 kilowatt hour at 1 o'clock, I end up owing nothing. And assume I am signed up for time of day metering. What that means is the price of electricity is 15 cents a kilowatt hour between 9 a.m. and 9 p.m. and 2.5 cents a kilowatt hour at other times. Now this is great for solar because 9 a.m. to 9 p.m. is when the solar panels are producing energy, and at night they're not, so I don't really care. In MATLAB, I can convert kilowatts into dollars as follows. I'll first convert the megajoules to kilowatts, times 4.7376. I then have to keep track of the time of day. I've got 700 data points. If I take the time mod 24, that'll go 0 to 23, 0 to 23, 0 to 23. That'll tell me what time of day it is, 0 to 23, 0 to 23. In terms of pricing, I'll create a new variable called peak. The peak time, well, that's what our or mod does. Mod just counts 0 to 23. Peak is 1 if I'm at peak demand. That's between 9 a.m. and 9 p.m. And off-peak is the other times. So the price per kilowatt hour here is a variable I'm going to create that's same size as my data, but it's going to be at the peak times 15 cents a kilowatt hour, off-peak times 2.5 cents a kilowatt hour. So this converts kilowatt hours to dollars. Then add them all up. So the value of the electricity at any given hour is price times kilowatts. And again, I've got to use that dot notation. This isn't a matrix multiply. This is just element by element. At each hour, what's the value of the electricity? At each hour, how many kilowatt hours did I produce? Add them all up, I get $355. So that's how much energy, the revenue I produce over the month of April 2023. In terms of how long it would take these panels to pay for themselves, well, take the price of the panels divided by the dollars per month. It'll take 53 months for the panels to pay for themselves at 12 months a year. It'll take about 4.45 years for the panels to pay for themselves. So that makes this actually a pretty good deal economically. This is a little bit off. It doesn't take into account installation costs. It doesn't take into account the 20% tax credit you get to buy and install the solar panels. This is just the panels themselves. So if you live over in Minnesota, Solar panels are actually a really good deal, especially if you can install them yourself. They'll pay for themselves in 4.4 years based upon this analysis. Also, this analysis isn't entirely right because all months aren't the same as April. If I really wanted to do it, I would take a full year's worth of data, which is available on ENDON. I didn't do that because, well, if you can do 1 month of data, you can do 12 months of data. It's just more data. The point behind this course is using MATLAB, but it's for real application. This actually says solar energy is a pretty good deal in Minnesota. So that was the first case. Suppose instead you live in Cass County, North Dakota, and you get your energy from Cass County Electric. With Cass County, you pay 11 cents a kilowatt hour for the energy that you use, and if I overproduce, I get 2.8 cents a kilowatt hour for the energy I put back on the grid. If I take the average of that, again, for lack of anything better, let's suppose half the energy I produce I use, half I put back on the grid, so that half is kind of a number pulled out of the air. The net result is the energy I produce is worth about 6.9 cents a kilowatt hour. And MATLAB, I can figure out what the worth of the electricity is. I've got the kilowatt hours, the sum of that. Each kilowatt hour is worth the same, 6.9 cents. So I get $168 if I live in Cass County. The number of months it takes to pay for itself is the cost of the panels divided by 168, 113 months, or 9.4 years. So again, that number's a little bit off. It doesn't take into account the 20% tax credit you get to install. It doesn't take into account the installation cost. It doesn't take into account if you watch the solar production, I could do the laundry when the sun's out, use more than half the energy you produce. Kind of a ballpark guess. But as a ballpark guess, this says that this is not a good investment from a purely economic standpoint over in Fargo, North Dakota. However, in Minnesota, solar panels right now are a pretty good investment. They pay for themselves in 4.7 years. And North Dakota, they don't. But 9.4 years is not that far away from 7 years. If the price of solar panels drops by 26% through tax breaks, price reductions, or whatever, then this becomes a good investment in Fargo. If the efficiency of the solar panels can be increased from 21.5 to 28.9%, again, this will be a good investment. If you take into account environmental issues, you might still want to invest in solar panels. And if you live somewhere that gets more sun than Fargo, North Dakota, or has more favorable policies, like net metering like Minnesota, you still might want to buy solar panels. So even in Fargo, North Dakota, a place not widely known for being sunny, solar energy is almost viable today. It will probably be viable very shortly. For example, if you go to the U.S. Energy Information Administration, they keep track of the price of solar panels in terms of dollars per watt, and the price is dropping pretty drastically. That's for a fixed system. If you have a tracking system, tracking systems produce 40% more energy than fixed systems. So you get that 26% right away. Tracking systems are solar panels that sit there and turn and face the sun. Those are a little bit more expensive, but they're dropping pretty drastically as well. So that kind of says that solar energy may or may not be viable today. Wait 2-3 years, it will be. So that's good news for electrical computer engineers. That means we got jobs. It's also good news for the environment. You can produce energy without producing carbon. Another question. What is the cost of solar energy on a dollar per kilowatt hour basis? Well, we can figure that out from our previous analysis. Let's assume the panels last 20 years. Again, the solar panels are made out of silicon. They're not going to fall apart or anything like that. What happens with solar panels is the glass on the front gets frosted. So suppose, let's just give it a number, like 20 years. They last 20 years. Probably last longer than that since solar panels have no moving parts. There's nothing to break. But let's pick 20 years. If the solar panels last 20 years, The total production from these panels, assuming everything stays constant, will be 24, 28 kilowatt hours per month, 12 months a year, 20 years, 582,000 kilowatt hours I should get out of these panels. And initial cost of $18,999, and that many kilowatt hours, means it's going to cost 3.26 cents per kilowatt hour. So in terms of how that compares to other energy sources, again from the U.S. Energy Information Administration, solar energy is right here, slightly more efficient or more expensive than coal, assuming no carbon capture. You just take all the pollution, dump it in the air. Slightly more expensive than nuclear and wind, but cheaper than gas, hydro, way cheaper than coal with carbon capture. So currently solar is right here, and the price is dropping. So a couple comments on this. Without any government subsidies, in 2023 the price of solar is almost the same as coal without carbon capture, meaning you dump all the waste into the atmosphere. It's about 90% cheaper than coal with carbon capture, assuming carbon capture works, which is a big question. That's one of the reasons that you're seeing so many solar farms going up across the country, especially over in Minnesota. For example, this is a solar farm over in Mapleton, Minnesota. Some analysis has actually shown that it's more profitable to put up solar panels than it is to grow corn ethanol. Plus, you produce electricity without producing any carbon dioxide, without any greenhouse gas pollution, and it provides jobs for electrical engineers. So that's one nice thing. So with our previous lecture, when we looked at global warming, that's kind of concerning. There is something we can do about it. Solar panels are one thing we can do. Well, there are other things as well. You can produce wind energy. So if you go to end on, so again, going back to Rugby, North Dakota, there's all sorts of data here in end on. One of them is wind speed. So if I look at the average wind speed, there's other ones as well. Average wind speed is what we care about. With that, I can look at how much energy a wind turbine would produce. So let's pick a wind turbine. This is one of the largest wind turbines you can buy today. It's a Vesta 7.2 megawatt wind turbine. It produced 7.2 megawatts of electricity at peak production. The blade is 172 meters diameter. It's bigger than a football field, almost 2 football fields. The hub is 114 to 199 meters above the ground. Extra one there. And cost about $9.36 million to install, including the tower, generator, pad. That's from the U.S. Energy Information Administration. It's about $1,300 per kilowatt for a wind turbine. So with that, let's investigate how much energy this wind turbine would produce on an hour-by-hour basis if installed in Fargo, North Dakota, how many pounds of coal that would offset, and how long you'd have to wait until the wind turbine pays for itself, i.e., is this a good investment from a purely economic standpoint? Well, again, the first step is to get some data. If I go back to end on, select Fargo, and average wind speed on an hourly basis, it's like over here, I can do pick your favorite town, doing Fargo, wind speed average, and let's just do the last 2 weeks. Here's what the data looks like. If I export to a CVS file, I can copy and paste and put that into MATLAB. So in MATLAB, I'd say wind equals start of matrix, paste, end of matrix. There's my data. I can now plot it. The hours will go from 1 to the length of the data. If I plot hours divided by 24, that gives me day versus wind. And here's what it looks like. So there's the wind speed on an hour-by-hour basis over 30 days of April 2023. And here this axis is meters per second. Now, as you can see, the wind blows and calm, blows and calm. Generally, it's pretty windy here in Fargo. With that, let's convert that to kilowatts. How much energy would this wind turbine produce? Well, the hub height is about 180 meters off the ground. The wind speed is actually higher at 180 meters than it is at the ground. If you look at the data from end on, it's recorded at 2 meters, 6 feet. Part of the reason is cost. They're really trying to do crop studies for end on, want to find out what the weather's like near the surface. Are the conditions right for fungus growth? Well, we actually want to use this data for a wind turbine. So if you think about a kite, the wind blows stronger as you get higher and higher in elevation. So if you go to Wikipedia, I can convert 2 meters to 180 meters using a constant. From Wikipedia, the wind speed follows roughly this equation. And assuming smooth, flat terrain, 180 meters is about 2.2 times stronger than 2 meters. So to convert to the wind at 180 meters, multiply by 2.2. And not exact. If I'd actually want to do a study for utility, I would take better data at higher altitudes, but this is what we got. Once I know the wind speed, I need to figure out how much energy the wind turbine produces. Now, if you look at a wind turbine, the power curve kind of looks like this. It takes a little bit of wind for the wind turbine to kick in. Then it goes up and then becomes flat. The reason it becomes flat is the generator only can produce so much energy. You've got to size the generator somehow. And if I make it unlimited in size, then the cost is unlimited. If I limit the size of the generator, then anything above that amount of energy, it just can't produce. The generator's not that big. So that's kind of what it looks like. If you go to Vesta's website, you can find the power curve for this wind turbine. So at a couple different points, there's the energy it produces, and above 13 meters per second, it's a constant, 7.2 megawatts. So let's come up with a function. I'll pass the wind speed, and it returns the kilowatts, following this curve. One way to do that is what we did last week, do a curve fit. I've got my data points between 3 and 13. Here's the kilowatts between 3 and 13. Let's do a cubic curve fit. So for this part, I've got a cubic. There's my basis. Here's my least squares curve fit. And then for each data point, I can convert that to kilowatts. So what this does is this sets kilowatts to be the same dimensions as wind. So every hour, I've got wind speed data. Every hour, I want kilowatts. At each data point, if the wind is less than 3 meters per second, I produce 0. If it's bigger than 13, I produce 7,200. That's the if-else if. And if all that fails, I use my curve fit. So here's my cubic times my basis. That'll give me this curve. So this is a function. That's kind of one of the uses of MATLAB. I've got a function that'll convert wind speed to kilowatts following this data. Now the first thing I might want to do is check how good is my curve fit. So in this case, I'm going to have, suppose the wind goes between 0 and 15 meters per second. Do the power curve at each data point. So what this graph does is the actual data is the red line. My computed power curve is the dotted line. So this is what I'm calculating. Between 0 and 3 meters per second is 0. Then I've got my cubic right here. Above 13 meters per second, it's a constant. That seems to match my data pretty well. So, okay, I think that function's all right. Given that function now, let's convert wind speed to kilowatts. And to do that, I'll take the wind speed times 2.2. That converts the wind speed from 2 meters altitude or elevation to 180 meters. At each point, convert to kilowatts. and then plot hours versus kilowatts. And I'm actually going to do hours divided by 24, days versus kilowatts. So this is how much energy I would be producing with that wind turbine over the month of April 2023. And if you notice, it's variable. That's the wind. The wind doesn't always blow. Sometimes I get full power, sometimes you get less. That's just how the wind is. The total energy produced is the area under the curve, or add it all up. So with that data, I can now start looking at what it means. If I take the average of the data, this is a 7.2 megawatt wind turbine. On average, it's only producing 3.3 megawatts. That's because the wind isn't always blowing. If I want to come up with the energy equivalent, or size equivalent for this wind turbine, it's about 3.3. So this is about 40% utilization. So the effective energy produced from this wind turbine is about 40% of the nameplate. The nameplate is 7.2 megawatts. It's effectively 3.3 megawatts at the site. The total energy I produce will be the sum of the kilowatts. Add them all up, I get 2.4 million kilowatt hours. It's a big number. Questions and answers. How much energy would this produce if installed in Fargo, North Dakota? Well, that's the sum. Over the month of April 2023, this wind turbine should produce 2.4 million kilowatt hours. How many pounds of coal would this offset? Again, same analysis. It takes about 1.78 pounds of North Dakota lignite to produce 1 kilowatt hour. So this would offset 4.3 million pounds of coal every month. Yeah, that's a huge number. How long does it take for the wind turbine to pay for itself? Well, again, it depends where you live. Suppose you live in Moorhead, Minnesota, and you have peak billing. In that case, the energy is worth 15 cents a kilowatt hour during the day, 2.5 cents a kilowatt hour at night. In MATLAB, I can do that. Here's the power in kilowatts. There's the time. Hours is the mod of time, 0 to 23, 0 to 23. At peak time, that's between 9 a.m. and 9 p.m. Off peak is 1 minus peak. So this is the price of electricity at that time that I produce it. The dollars that it's worth is the kilowatts times the price at that time, add them all up. I would be producing $253,000 over in Minnesota in terms of payback time. If it costs $9.3 million and I get $253,000 per month, it's going to take 36 months or 3 years for this wind turbine to pay for itself. That says from an economic standpoint, this wind turbine is a really good investment. Option number 2. Suppose you live in Fargo, North Dakota. Here you get 6.9 cents a kilowatt hour on average. So the revenue would just be the kilowatts times 6.9 cents a kilowatt hour, add them all up, $169,000 over that month. It now takes 55 months, or 4.6 years, for the wind turbine to pay for itself. But that's still a good investment. If it takes less than 7 years, it's a good investment from an economic standpoint. If you live elsewhere in the country, elsewhere, electricity averages 15 cents a kilowatt hour, much higher in California. So if you live elsewhere where you get more for your electricity, then it's an even better investment. Finally, how much does it cost to produce electricity using wind energy? Well, if I assume a 20-year life cycle, which is typical for generators, the wind, and assume the wind each month is similar to April 2023, which is kind of dubious, but let's just go with it. The cost per kilowatt is then, this is how much energy it produces each month, 12 months a year, over 20 years. This wind turbine should produce 586 million kilowatt hours over its life. At $9.3 million cost, it's 1.59 cents per kilowatt hour. That ignores operation and maintenance cost, just the installation cost. So in comparison, wind is about 1.59 cents a kilowatt hour. Nuclear, about 2.4 cents. Coal, solar, gas. Wind is hands down the cheapest way to produce electricity. And that actually kind of makes sense. If you think about a coal plant, with coal, you've got to dig up the coal, crush the coal, clean the coal, burn it, produce steam. Steam spins a turbine that spins a generator that produces electricity. With wind energy, you skip all that. You got the wind, spins the generator, produces electricity. So you took out 90% of the process. So it's kind of unfair. Of course, wind's cheaper. Plus, there is no fuel cost in wind. So if you have, basically 80-90% of the coal plant is gone and you have no fuel cost, sure, wind's going to be cheapest. That's kind of expected. So it's really hard to compete with wind. That's one of the reasons you see so many wind farms going up in North Dakota, South Dakota, Minnesota. It is a really cheap way to produce electricity. And here's kind of a sidelight. How much energy could we produce in North Dakota if we just used wind energy? Well, the National Renewable Energy Administration has actually looked at that. North Dakota has the potential of producing 1.1 terawatt hours of electricity per year. That's enough to supply 25% of the entire nation's energy needs just from North Dakota. If you get 10 cents a kilowatt hour, that would produce $118 billion each year for the North Dakota economy. In Minnesota, they have an oil revenue. Every resident, or actually Alaska. In Alaska, they have oil revenue. Every citizen of Alaska gets a $1,000 check every year as their share of the oil resources the state has. In North Dakota, we conceivably could give every resident $157,000 a year revenue from the wind resources that we have. Let's see. $118 billion is more than double the entire GDP for North Dakota. So if you take the revenue produced from agriculture, ranching, industry, hospitals, insurance, universities, everything in the entire state, add it all up, it is less than half of the potential energy we could get just from our wind. And you actually get more than that if you got 15 cents a kilowatt hour, which is the national average cost for electricity in the United States. So wind energy is a big deal. And there is some talk about bird deaths. Well, wind turbines kill birds. Well, that is true. Wind turbines kill about 234,000 birds a year. However, comparing that to other causes of bird deaths, cats kill about 100,000 million, 2.4 billion birds a year. The glass in buildings kills 559 million. Vehicles like cars, poison, electric lines, communication towers, electrocutions, oil pits, all kill more birds than wind turbines. This is not really a terribly significant number. It does happen. They do try to avoid bird deaths with wind turbines, but in terms of the bird population, this ain't the problem. It's our little furry friends. So in summary, MATLAB, again, is a really useful tool. With MATLAB and the internet, you can analyze data yourself. Again, you don't have to rely on experts. You can analyze it. With MATLAB, you can evaluate how much energy a solar array would produce for you. You can evaluate how much energy a wind turbine should produce. And at present, solar energy is one of the least expensive ways to generate electricity, and the price is dropping. Wind energy is the least expensive way to produce the energy. Solar is going to compete with it fairly shortly. And this is actually really good news. It's good news for electrical computer engineering majors. That means we got jobs. It's also good news for the planet. It says that you can produce carbon-free electricity, and it's also economic to do so. So that should be enough to get you started on this week's homework. The kind of main thing to take from this is MATLAB is really useful, and you picked a good major. We get to have fun. I like to say that we build toys, but we build toys for purpose. and the stuff that we do might save the planet. So that's lecture number 5 for ECE 111, Renewable Energy.